Okay, so we're going to be going over 4, 5, and 6 here in the recording. And just a quick announcement, we're going to be doing a purely virtual midterm 2 review session on Sunday. So expect the worksheet to be posted sometime on Sunday, most likely. This weekend is super busy for me, which is unfortunate because I'd like to be super like able to get to emails, but just like by nature of my schedule, I might be able to slow on turnaround. So really try to you know, email your professors or just Google it and try to figure it out. But of course, email me if your confusion persists. So yeah, Sunday we'll do a review session. Um, and yeah, I think that the material has been posted for what to review and they gave you an idea of what questions to expect. So let's just dive into this question here, Q4. Question 4, here we have, an equilateral triangle. The index of refraction is 1.6. We want to determine the exit angle. Question in the chat. Oh, time on Sunday, probably in the evening, but not that late. But more on that soon. Like I like to do like around 4 to 6 but we'll see. In case we have this triangle. Here, I'll pause the recording so you guys don't have to watch me draw and mess up and draw and mess up. Okay, so question 4 is all set up here. We have this ray that's moving through this prism. We know the index of refractions and everything here. And it's just like a fun day with trig when you try to solve these questions. Just one thing I want to note is that this is called the normal right here. This line right here, it's called the normal. And whenever you have your ray entering like, like water or this prism or whatever you want to call it, the normal is always perpendicular to whatever it's entering. So in this case, we're entering this triangle, right? So we notice it's perpendicular. There's a 90-degree angle between the normal and that triangle. And then same thing, right? Like just to make this very clear, like if we have like water like this and someone's like putting a laser into the water like this, the normal here is like this. And the key thing to note here is the angles of that you plug into Snell's law, right? I expect you to know Snell's law already. The angles you plug into Snell's law must always touch the normal. So we'll call like theta 1 right here and theta 2 right here. So these are the angles you plug into Snell's law and get out of Snell's law. That's really important. It's not this angle between the surface and the ray. It's the one between the normal and your ray. So that was just kind of an aside, but really underlies the importance here. So when we first come into the system, we have a ray entering in. We start off with Snell's law. Using Snell's law, we're going to be able to solve for this angle right here. Let's call that theta 2, okay? And remember, that's between the normal and that's the normal and the ray. So we set this up. I'm going to call n air NA just to save time. Sine theta 1 is going to be equal to 45 because they gave us that. And that's equal to the index of refraction within the prism. Sine theta 2, solve for theta 2. I'm not going to go over how to do that, but it's just inverse sine. You'll have sine 45 over 1.6. That'll come out to 26.23 degrees. Okay, and now you have 26.23 degrees. But what we need to be able to find this angle of interest is this angle here. Right now, we don't have enough information to solve for that. But what do we know? We know that the normal is perpendicular to our surface of interest, 90 degrees. So we know right here there's a 90-degree angle. Therefore, we can solve for this angle right here. Let's call it theta 3, because 90, oh, sorry, I don't know what's going on with me today. That's my first step. Second step, 90 minus theta 2 is going to be equal to theta 3. Now, if you went to my SI session this week, this is about to get super repetitive because, we really hammered this, this point in. Okay, so, we know how to find theta 3. And we also know that this is a 60 degrees right here because it's an equilateral triangle. Therefore, we can solve for this angle right here. Let's call it theta 4. And why we can solve for that is because it's a triangle. So therefore, it's 180 degrees. So to solve for that theta 4, we'll say that, we have 60 plus theta 3, theta 3 plus theta 4 is equal to 180. We know what theta 3 is equal to. We just solved for that, right? So we can now just solve for theta 4. and theta 4 is going to be equal to 56.33 degrees. Okay, sorry, my handwriting seems to be getting worse on the iPad. I got confident and now it's gotten worse. And then again, per the same logic, we're going to be able to solve for this angle of interest here, which we'll call theta 5, right? And remember, the angle we need to plug into Snell's law is the angle between our ray and the normal. So it has to be this one. You can't plug in theta 4, you'll get something wrong. And what's the relationship between theta 4 and theta 5? Well, that's going to be equal to 90 minus theta 4 is equal to theta 5. Theta 5 comes out to be equal to 33.77. And you can now solve for that angle of interest using Snell's law again. We'll call this part 5. And prism sine theta 5, we just solved for that, is equal to the index of refraction in air, sine our angle of interest, solve for the angle of interest in the same way we did in part 1, and that's 62.8 degrees. All right, that sounded like I was a Khan Academy video there. So let's see if there's any questions. Okay, so here we have this right triangle, index of refraction given. We want to find the largest angle theta such that there is an internal reflection when the light ray hits the hypotenuse. Okay, so like theta, in the case that there's total internal reflection, that means we're going to need to plug in a sine 90. And I kind of teased that out already, what that looks like. It's going to be like skimming there along the edge and like bouncing back and not going to be behaving as we would like have observed in a normal case. So we set up our Snell's law again, right? We'll say n in the glass there, right? It's glass. Or prism, glass, whatever. Let me say P for prism. And A for air. So n prism sine theta 1. And what's our theta 1? Again, that's going to be the angle that is touching right here, touching the normal, is equal to n air and then sine. What do we plug in? 90, because we have a case such that there is an internal reflection when the light ray hits that hypotenuse there. So work this out, you'll solve theta 1 is equal to 40.5. Okay, well now we want to find what this angle is. And if you have a good eye, you'll be able to solve that angle because you know what this angle is. Those are the same angles. It's the same triangle. So this right here can also be called theta, right? And what's the relationship between theta then and theta 1? Well, we know it's perpendicular. So here it's 90 degrees. So what we can say is 90 minus theta 1 is going to be equal to theta. And that theta is going to be our angle of interest. So therefore, it's going to be equal to 49.5 degrees. Oh, wait. I did a decimal thing here. 90. Where did I mess this thing up? 49.51. Is that right? Seems, yeah, okay. 49.51. I think I messed up a decimal there. Oh, it's fine. I think it was in the first part. Okay. Cool. Any questions on that?